Welcome to the 30th video of Quantum Mechanics Done Right, the shortest path from novice to researcher. In this video, I'm going to tell you about the epilogue to the book. I want to start by congratulating you. We did it. We got through this book. We learned how to do quantum mechanics. We learned how to do quantum mechanics right. And not only is this something that a very, very small fraction of people in the world actually know, you really know quantum mechanics at a very high level. And I would say that you know it well enough that you could do research with someone else who can guide you into how to do that work. Why do I know this? Because I've done this with numerous people who have even read just a fraction of the book. They were actually ready to do research. So congratulations. It's a long journey. You really did a lot of stuff, and you really now know a ton of things about quantum mechanics. So congratulations, you are now officially a quantum mechanic. When I launched my MOOC, Quantum Mechanics for Everyone, at the end of the video, at the end of the class, I had a video where I was wearing this little smock. It is actually a quantum mechanics smock, or at least I jokingly call it a quantum mechanics smock. And in the process of the video, I took the smock off and I handed it to the audience, indicating that now you've earned the privilege to wear the smock itself and call yourself a quantum mechanic. So if you've gotten through the book, congratulations, you are now a quantum mechanic. So what is next? If you want to go on and study the next area, which would be quantum field theory, you almost certainly are going to have to learn a bit more math. It's very difficult to get through quantum field theory and not understand a bit of complex analysis. And to get to complex analysis, you really have to go through calculus. So there's a long haul of math that you would need to learn in order to do things that are much more advanced. This is also true if you want to go into many-body physics. The most common language of many-body physics is Green's functions, and in order to work with Green's functions, you do need to know a bit about complex analysis and work with complex analysis. Sure, there are some things that you can do that don't require it. You could do work on, let's say, exact diagonalization studies of frustrated magnetism, and you probably don't need to know very much more advanced math. But in general, if you want to continue your studies, you are going to need to learn a lot of more advanced math. And I think it's useful too, because the math really helps you do things that are more complicated. So I encourage you to be able to both learn more math and learn more quantum if that's something that you want to do. As I mentioned before, you now have all of the skills. In fact, you have a ton of skills. You're actually able to perform mentored research. I say mentored research because oftentimes it requires having someone who has the experience to know what are good problems to work on, what are problems that you have the skills that you need in order to complete them, and so forth. So it really is mentored research that we're talking about you're being able to do. I would say at the level of what, say, an undergraduate senior is, who is going to do a senior research thesis and do that with a faculty member who's going to guide them on the research project, you actually have the skills to be able to do that on a quantum mechanics topic. You might also want to learn about the conventional way of doing quantum mechanics. I think it is useful simply because this is the language that many other people will describe. I think you'll see why it's kind of clunky and doesn't work so well. You definitely will see, if you go beyond, why a lot of the stuff that you learn you can't use in future work. But I think there is some benefits to it, and it is useful to learn about scattering theory. I don't talk about scattering theory. It is useful to learn about perturbation theory. I didn't really teach much about perturbation theory. So there are some useful things out there still in quantum mechanics after you get through the calculus hurdle if you've been doing this book using just the high school level math. You can also study more advanced ideas like solid-state physics and statistical mechanics and so forth. There's lots of interesting stuff there, nuclear physics as well. Lots of interesting stuff there. Many of them will assume you've taken classes that have studied it the conventional way, and so you might need to do a little bit of reviewing about the conventional way of doing things to get into being able to understand it. I think the one major thing that I don't cover that is sort of expected that you know is knowing what a Dirac delta function is and how that enters into completeness when you're working with continuums of states. That is something that we haven't really covered because we didn't need it, but that is something that you sort of expected to know. So if there's one thing you would need to pick up to then become comfortable in working with this other more advanced material, that would be one of the things. But many of the things that you would cover in a solid state physics course or statistical mechanics course, we've already covered a lot of the things that are related to it, and we've covered things that they don't even get to in those classes, like decoherence or the Hubbard model or other things like that. So you're actually in pretty good shape to learn a lot of that material. Hey guys, let's do quantum right.